Alright, we're still doing trig identities. This is pre-calculus, semester 2, unit 4, algebra 2, semester 2, unit 4, or unit 5, excuse me, for algebra 2. Not as much in algebra 2, so a little bit slower going. Sine of 4x equals 1/2 over the interval 0 to 2 pi. They want to know how many solutions there are. So the first thing we look at is when is sine of x, when is just regular old sine of x equal to 1/2? We know that sine of pi over 6 equals 1/2, and we know the sine of 5 pi over 6 equals 1/2. Alright, so those are the only two scenarios between 0 and 2 pi where sine equals 1/2. Cool, so we can say our answer's 2, we can move on, right? Done. Well, not quite. So because we are changing the sign argument, we are multiplying by 4, we need to adjust our arguments down here. So we know we have 4x. When does 4x equal pi over 6? Well, divide by 4, that's when it's pi over 24. So we'd actually plug a pi over 24 in. And then for the other one, it would be 5 pi over 24. Now, what we need to remember now is that we're going to 2 pi, but now we have a denominator of 24. So if I have a denominator of 24, what's 2 pi? Well, 2 pi is going to be 48 pi over 24. So any value that is under 48 pi over 24 is within one revolution of the unit circle. So it's within 0 to 2 pi. So 48 pi over 24 is equal to 2 pi. Now, since we know we're changing this by 4, and we're basically making that pi over 6 a smaller fraction, right? Because of this, we're multiplying by 4, is that our pi over 6 is actually quote-unquote equal to, it's not really, but it's equivalent to, directionally, pi over 24. Alright, so what we're going to do is I'm going to go to my unit circle, and pi over 6 is here. What I'm going to do is I'm going to do full revolutions, and I'm going to keep doing it. So I have pi over 6, which is really pi over 24, right? Because that's what we were working on. We were working on pi over 24. Well, if I add to that, and we're going to go back, we're just going to keep it simple. We have pi over 6. If I add a full revolution, which in this case, going back to normal, would be just a 12 pi, so I'm just doubling the denominator. I'm adding a 12 pi. It's going to be 13 pi over 6. And we know that if we multiply this by 4, so if we did 4 times 13 pi over 6, that's equal to 13 pi divided by 24. And that 13 pi divided by 24 is still well within the 2 pi range, that 48 pi over 24. So we know 13 pi over 6, we're good. So as long as this numerator is below 48, we're good. So I'm going to do another full revolution for pi over 6. Well, I went to 13, so I'm going to add 12 again. That's now 25 over 6. And I'm going to go ahead, I'm going to add 12 again. That's 37 pi over 6. Cool, I'm going to add 12 again. Oh, I get 49. Well, I'm not going to write 49 down. Why? Because 49 is not within 48, right? 49 is bigger than 48. So it's outside of the 2 pi range. But what I just discovered was 4 answers that I could plug in that would make this equation equal to 1/2. So pi over 6, 13 pi over 6, 25 pi over 6, and 37 pi over 6. These all would make sine of 4x equal 1/2. Every single one of them. How did I do that? I had pi over 6. I discovered that with this multiplying by 4, it really is with pi over 24. And I know that 2 pi, if I have the denominator of 24, is going to be 48. So as long as I keep going to full revolution, so I'm in the same spot in the unit circle, and I just add 12, I'm in the same spot. As long as I'm within 48, I'm under 48, I'm good. So I found the 4 answers for pi over 6. Now I'm going to do 5 pi over 6. I'm going to do the full revolutions for it. I'm going to add 12. So we have 17 pi over 6. I'm going to add 12 again. That's going to be 29 pi over 6. I'm going to add 12 again. It's going to be 41 pi over 6. If I tried, and that shouldn't be, this is the pi. And if I try to add it again, I would get 53, which is again is above 48, so I can't use it. So for each of these values, there were 4 answers that would satisfy. So the total answer here is 8. That's our answer for this problem. So what I did is I was given this problem, sine of 4x equals 1/2, and they wanted me to find all the solutions within the range 0 to 2 pi. Well, the first thing I asked myself is, when is sine 1/2? In the unit circle, it was pi over 6 and 5 pi over 6. All right, so then I had to adjust. Well, what is my x value that when multiplied by 4 gives me pi over 6? So I did 4x equals pi over 6. I did 4x equals 5 pi over 6. And in each situation, I got pi over 24 and 5 pi over 24. And knowing that if I go a full revolution around the unit circle, if I go to 2 pi, I just double the denominator. Well, that 24 becomes a 48. And that tells me I can keep going around this unit circle as long as my numerator stays under 48. So I went to pi over 6, I added 12, I got 13 pi over 6, it's under 48, that's good. I added 12 again, 25, under 48, good. Added 12 again, and that's 37. That's under 48, that's good. If I try to add 12 again, I get 49. And it'd be too much. Now, why did I choose 12? Well, the denominator is it's 6, it's pi over 6. Well, I double 6 is 12. That's one full revolution. So I'm able to add 12 or just double the denominator, and that will give me one full revolution. I did the same thing for 5 pi over 6 to 17, 29, and 41, and they all worked. Gave me a total of 8 answers. Oh, that was probably a little sloppy of an explanation. Hopefully it made a little bit of sense. All right, so this one. All right. This I think is the last one. So we have 1 minus cosine 6x equals, we don't know. Well, what I'm going to say is, where are we at? All right, cool. So what I will see, there we go, is I have a couple identities. I have cosine of 2x equals, well, it could equal 2 cosine squared of x minus 1, or it could equal 1 minus 2 sine squared of x. It actually could equal cosine squared x minus sine squared x, but I don't see how that's going to make too much sense for us here. I guess it could. We'll try it. I'll do all 3, I guess. No, I don't. That's just going to be wasting our time. Who am I kidding? Alright, so with this, so I have cosine of 6x. So what I really have on this cosine, I'm not looking at it like I have a cosine of 6x. I'm saying I have 1 minus cosine 2 of 3x. So instead of writing as 6x, 2 times 3 is 6, I kind of separated them. That gave me this little double, that gave me this double angle by making it a 2. So now my theta is essentially a 3x. Alright, so now I can just plug it in. So I have 2 possible scenarios here. I'm okay with a 2 cosine squared. Instead of x, I'm going to write 3x minus 1. This one would be a 1 minus 2 sine squared. Well, my x is a 3x again. Alright, so these 2 scenarios are true. So if I go back to my original equation, I'm going to go ahead and write that down here again. I have 1 minus cosine of 6x, and we want to know what it equals to. Well, I think we have 2 different opportunities, 2 different possibilities here. I'm going to do 1 with the cosine. So I have 1 minus 2 cosine squared sorry, that should be in parentheses, 2 cosine squared 3x minus 1. Alright, if I distribute it, this is going to be a 1 minus 2 cosine squared of 3x plus 1. So this is going to be a 2 minus 2 cosine squared 3x. So I just plugged it right on in what we already calculated. I made sure I put parentheses because there's a minus sign there so I could distribute. I distributed that minus sign and then I combined my ones. My other possibility here is going to be 1 minus, well, parentheses 1 minus 2 sine squared 3x. And I'm going to, same thing, I'm going to distribute. So this is now going to be 1 minus 1 plus 2 sine squared 3x. That cancels. I have 2 sine squared of 3x as my final answer. Both of these are equivalent. I think Apex is going for the one in the blue, but we'll see at the problem. So these two are short. Again, the idea here was I wanted to kind of change this. This 6x, I kind of saw a double angle right away. So I kind of actually started off just doing with the double angle, but I see it as 1 minus cosine 2 times 3x. So I'm kind of separating this. And then I kind of wrote out my two double angle formulas, and I kind of solved both of them just by plugging and distributing.